Okay, so we are continuing on in our section on descriptive statistics. Okay, and descriptive statistics is all about being able to describe data. So we want to describe the data we have collected. And that could be describing them with words, with pictures, and with numeric summaries. Okay? And the way we describe our data will depend on whether we have collected categorical data or numeric data. Okay? So let's start off with summarizing or describing categorical data. Okay. Okay. So you have to imagine that when we have collected our data, so we'll say, imagine we have collected some data, and part of the data that we have collected is a categorical variable, okay? At least one of the variables is categorical. Okay, and so for example, you could say, just pretend we walked around one of the parking structures. Okay, so we'll just say we went to a parking structure, and we collected information on the make and vehicle type. Okay, so collected all right, so for example, in our data table, we would have, car 1. This one is a Honda, and we'll say it's a sedan, okay? Like a compact car, doesn't matter, okay. And then, so this is the make. And over here we have type. Okay, car 2, let's say it's a BMW, and it's a coupe. Car 3, maybe a Ford truck, okay, etc., etc., etc. Okay, and so we can summarize this. So, let's say we have 100 vehicles total. Okay. We can summarize with a frequency table. So this will actually, we can summarize one variable. And so we might just pretend that we'll say we saw some Hondas, some Fords, I know there are more vehicle types or vehicle manufacturers. So my apologies if I leave your brand off. All right, and I'm just going to say other, okay? I know there are many more. And I'm just making up numbers here. And but I have to count, so 18 plus 12 plus, okay, so that means we have 21 for the total. Okay, so that's summarizing one variable with a frequency table. And I think this is rather straightforward. And if we wanted to display this, we can display this with a bar chart. And so with the bar chart, the vertical axis will represent the frequency. Okay, and the horizontal axis will be our different categories. All right, so Honda gets a bar that goes up to 18. Something like this, okay? Okay, so this is the bar chart. All we've done is we've taken these numbers and put them, you know, the heights of the bars represent the frequency there. Okay, the thing about a bar chart, excuse me, is, this is stats 10. So the thing about a bar chart is that the arrangement of the bars don't matter. So if you wanted to put them in alphabetical order, that's completely allowed. If you wanted to put them in order from shortest bar to tallest bar, or tallest bar to shortest bar, that's also fine. If you just wanted to arbitrarily shuffle them around in some other way, that's fine as well, okay? It will still display the same information. So the ordering of the bars does not matter when we're talking about a categorical variable. It might make sense to talk about this concept of variation in a categorical variable. Okay, and variation overall is this concept of, are the values that we see, are they similar to one another, or are they quite different from each other? Okay. So similar would indicate low variation, or are the values very different from each other? Okay. All right, and so, you know, let's imagine there were two parking lots, and let's just, for simplicity, let's say vehicle class, we'll say you can either have sedans, SUVs, or trucks. Okay, and I know there are more types of cars, but let's say we have, so this is parking, we'll say this is lot 1, and then over here we've got lot 2. Okay, so we have sedans, SUVs, and trucks. Okay, so at lot 1 we have 30 sedans, 31 SUVs, 30 trucks. Okay, and at lot 2 we have 5 sedans, 10 SUVs, and 60 trucks. Okay. All right, so I'm going to just create a bar chart. So this will be for lot 1. Sedan, SUV, truck, lot 1. The bar chart looks kind of like this. And then for lot 2, we have sedans, SUVs, and trucks again. Okay, so sedans, there's only 5 of them. SUVs, we've got 10 of them. And then trucks, we've got 60. Okay. If we were using clickers, I would turn this into a clicker question, but we're not going to do that today. Which lot has more variation in the vehicles that we see? Okay. Okay. What do you guys think? Lot 1 or lot 2? Who thinks lot 1 has more variation? Okay, who thinks lot 2 has more variation? Okay. All right, well, the answer is lot 1 has more variation. Okay, let me, I'm totally serious, okay. All right, so just, I mean, you don't have to close your eyes, but just imagine walking to lot 1, and you look around, and what are the different cars you see? Okay, you see a bunch of sedans, you see a bunch of SUVs, you see a bunch of trucks, okay? Now imagine walking over to lot 2, and then you look around, and what do you see? Trucks. You just see trucks, right? You're like, well, man, everything's a truck here. And then you have a few sedans and a few SUVs, but not really, okay? So as far as variation, or, I mean, we could even think of it as, I don't want to say this is a definition of variation, but diversity kind of gets at this notion of variation as well, as far as categorical variables. If you think of lot 2, and maybe, the types of vehicles that you see there, there's not a whole lot of variation. It's almost all of the cars there, or vehicles, are trucks, okay? And so this one has less variation because one category is very dominant over the other categories, okay? So when one category or a few categories are very dominant, when one category is or a few categories are very dominant, that means less variation. Okay, and if none of the categories are very dominant, or if all of the categories are equally represented, then that would equal a lot of variation. Okay, so high variation is seen when none of the categories are dominant. Okay, that's when we are talking about a categorical variable. Okay, it is true that if we were dealing with a numeric variable, we would say, 5, 10, and 60, those are quite different from each other. 30, 31, 30, these are quite similar to each other. So if we were talking about a numeric variable, yes, these numbers have less variation and these numbers have more variation. That's if we're talking about a numeric variable, but we're not. We're talking about a categorical variable, and when we're talking about a categorical variable, it comes down to is one of the categories very dominant over the others versus not. Okay. Let me just flip back. Here in our table, we collected information on 2 categorical variables. We can summarize that information, and we can summarize 2 categorical variables with what we call a two-way table. Okay, in a two-way table, all that is, it's a frequency table, but with basically categories on both axes. So we would have make along one side, and we would list off Honda, Ford, Chevy, Toyota, BMW, other. Okay, so this would be along one axis, and then on the other axis we would put the vehicle type. Whether that is, sedans, SUV, truck. Okay. Yeah, I guess we'll just say other also. And then you just populate this, right? So I don't know, we have 10, I don't remember what numbers I had, but we'll just say 15 Honda sedans and 6 SUVs, 1 truck, and 1 other vehicle type, and this is what, 22, I can't add 20, 23, okay, for total or something like that. Okay, and then we could ask, what percentage of Honda vehicles are SUVs? Okay, and our answer here would be 6 divided by 23, and we would get some kind of fraction. On the other hand, we could observe excuse me, count how many sedan types, or count all of these up, and I need to add these up. 15 plus 7 plus 4 plus 13 plus. Okay, and I have 57. And over here, I could ask a different question, and I could say, what percentage of sedans are Hondas? Okay, and over here, our answer would be 15 out of 57. Okay, and I don't know how many total vehicles we have. Maybe we have a total of okay, and I don't feel like filling out all of these numbers, but let's say we had a total of 180 cars here. one more question could be, what percentage of the vehicles are Hondas and sedans? And our answer there would be 15 divided by 180, you know, as some kind of percentage. And so while these questions look rather similar, you know, the number we put in the denominator depends on how the question is asked. You know, is it speaking of the total number of Honda vehicles, total number of sedans, or the total number of all vehicles? Okay. All right. So that pretty much covers what I want to say about summarizing and describing categorical variables. And now we'll talk about numeric variables. Okay, and so again, you know, the big picture idea is we're dealing with a sample of data, okay, and probably this sample of data has been drawn from a population, and but we still want to be able to describe the sample of data that we have, okay. And when it comes to numeric variables, I'll show you ways that we can display the numeric variables, and after we understand how to display the numeric variables, we can talk about describing the things with words, and then we'll take a look at some numeric summaries here. Okay. So first, we'll start off with some graphic displays for numeric data. Okay, and so our first tool will be what's called a dot plot. Getting ahead of myself. Okay, and with the dot plot, all we do is we begin with a number line, and then we place a dot at each observation. Dot plots are, you know, this is best for relatively small data sets. Okay. All right, so let's say we have, I don't know, you go to some children's ages in a family, okay? So you visit some family that has, you know, let's say they have 5 kids. All right, and the kids' ages are, we'll say 1, 1, 2, 4, and 15. Okay? So I don't know, we can make up a background story for this family. And so to create our dot plot, you just start off with a number line: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, and then all we do is we just put a dot at each observation. So I would put a dot at the 1, another dot at the 1. Here's a dot at the 2, a dot at the 4. And then a dot at 15. And this gives us a sense of kind of where our data lies. Okay. Where our data is, and also whether the data is spread out or not. Okay. And you could just imagine, I'm just going to make up another data set here with more dots without actually plotting them all. I mean, without writing out every single value. So you could have something that looks like this. Something like that, okay? And so we can see, there's a lot of values at whatever this is. I have no idea what these numbers represent. Just a made-up data set here. And so here's another example of a dot plot. Now we could you can imagine if the data sets get very large, we might not want to represent all of our values with their own dot, okay? And so the next idea we have is what we call a histogram. Okay, and so with a histogram, we put bars, okay, instead of dots. Okay, so this is better for slightly larger data sets. Okay, and instead we use bars instead of dots. So over here I would count how many I have. Here I have the frequency is 5 and 3, 3, 2, 1, 3, 6, 5, 3. Okay? And so this just becomes, I have a bar for the height or the frequency, 0, 1, 2, 3, 4, 5, 6. And across the bottom I put values 0, 1, 2, 3, 4, 5, 6, 7, 8. And we put bars at how high they should be. Okay, so starting there, I create a bar that goes out to 5. And for 1, I create a bar that goes up to 3. Same with 2. And right here we have a bar that's at height 2, a bar that's at height 1, and a bar that's at back up to height 3, up to 6, something like this. All right. I think you guys get the idea. Okay. And the kind of stylistically, the bar that contains 0 starts at 0, okay, and goes up to 1. Okay, so the bars aren't centered at the numbers, but this bar starts at 0 and goes up to, but does not include 1. Okay, so you could think of this bar as for the range, and are you guys familiar with the square and the curved brace to indicate it includes 0, and the curved brace to say up to but does not include 1 type of thing? Okay, and so that's why the bars aren't centered at each number, but rather kind of hangs out at these boundaries here. Okay, and so this is called a histogram, and it looks very much like a bar chart, except with the bar chart we said you could rearrange the order of the bars. With a histogram you cannot rearrange the order of the bars because the order or the arrangement of the bars is tied to the number line. Okay, so the is tied to the number line. Okay. If you have a lot of data, okay, so let's say we went to the DMV and there was like 100 people there, or maybe 200 people there, and we asked them, how old are you? Okay, what's your age? And so we're going to get some people who are aged 16 and 17 and 18. But then we're also going to get, maybe we find someone who's 37 and someone who's 38 and 39 and 54 and whatever. Okay, we're going to have a large range of values. It might not make sense to have one bar for every single age. So instead, we can also group our values together. Okay. And so, I'll just do it very quickly with this data set, but we could say, we can create what we call bins. And our bin maybe go up to 0, 0, 1, 2, and then we'll have 3, 4, and 5, and then we'll have 6, 7, and 8. Okay, and so now I've reduced the things, and then the next bin would go 9, 10, 11, and so on and so forth. And all I do is I would just count how many are in each bin. So I have 5, 3, 3. I have a total of 11 in that bin. At 3, 4, 5, I have a total of, 6 in this bin. And 6, 7, and 8, I have 14. And 9, 10, 11, I didn't even bother putting any values there. I have 0. Okay, and so in this case, our histogram would look like this: 0 up to but not including 3, up to but not including 6, and then 9, and then 5, 10, 15. I have a bar going up to this one goes up to 11. This one goes up to 6. And this one goes up to 14, or something like that. Okay, so here all we are doing is, depending on your data, it might make sense to group some of our values together so we have fewer bars to deal with. Okay, so we can also group our. So this histogram and this histogram represent the same data. This one just has, less detail on as far as the individual values go. Right. Is that good with everybody? How this histogram is going? In the textbook, it also covers something called a stem plot. And I feel like stem plots are one of those things that show up in textbooks, but rarely show up outside of textbooks. Histograms, I think, show up frequently outside of textbooks, but with stem plots, you have what's called the stem. And it might be something like this. And then you have what's often referred to as the leaf. Okay? And here we see this 1 and we see this 0, and the 1 with the bar 0 represents the number 10, okay? And then the 2 represents the number 12. So this first row, the first row represents the values 10, 12, 17, okay? And perhaps I have another set of values here. And so this second row represents 20, 22, 22, 29. Okay? And then this third row maybe represents 31 and 36. And this is what we would call a stem plot. Okay? And if you were so compelled, depending, if you have lots of data, you can further split it, and you can say, the first row will be through 10 through 14, and the second row will be 15 through 19. So in this case, our data, we would have 10 and 12, and then the 17 would drop down here. We would have 20, 22, 22, 29, 31, 36. Okay, so we could split each row into multiple rows. Okay. And the stem plot, when you do the stem plot, they are effectively like histograms. Okay, you could just imagine here I'm taking the stem plot and I would just rotate it. Okay. So we'll just take this thing and rotate. And now I have effectively what looks like a histogram. Okay. So by looking at kind of the way the stem plot looks, we can get a general idea of the kind of the shape of our data. And the stem plot has the added bonus of seeing the actual values that each data item took. But for whatever reason, again, I feel like we don't really see these too much outside of the textbooks. All right, I have to cover, so we have histograms to kind of, so just imagine we've produced a histogram for some kind of data set. And the histogram looks kind of like this. Okay. Now for simplicity, I might just say the overall shape of our data, looks kind of like this, or something like that, okay? And we could describe this shape, we can say, well, it looks kind of like a hill, but we have a little bit more technical terms. And in this case, we would say the shape of our data, or the distribution of our data, and we would say is unimodal. Unimodal means has one peak, and symmetric. Okay. And in this case, symmetric would mean that values that are extremely high, so if this is the middle, and this is values on the high end and values on the low end, symmetric means values that are extremely high are about as common as values that are extremely low. So the classic example of symmetric data is human height. Okay, so we often think and say human height is symmetric. Most people are kind of in this between 5 feet and 6 feet tall, or give or take a few inches there. Okay, most people are between 5 feet and 6 feet tall, or maybe a few inches higher, lower, or something around there. Okay, but yes, do we have extremely tall people? Yes, LeBron James, Yao Ming, these are on the extremely tall side. Okay, but you don't have very, very many people who are extremely tall. So some people are extremely tall. Okay, so we could think of some athletes or NBA players. And then on the other hand, some people are very short. So some famous people who are, short, Peter Dinklage, Warwick Davis, things like that. Some actors, and but they are probably about as the frequency of extremely tall and the frequency of extremely low are comparable. Okay, so some people are extremely tall, some people are extremely short, and they have similar frequencies. So that would be human height being an example of something that's symmetric. Okay. Other distributions, other data might look something like this. Okay, and we would call this right skewed. Okay, right skewed. For right skewed, the typical or the middle, let's see, maybe not there. Middle is somewhere around here. Most people are over here. So most people are over here. Let me just kind of move this over. And you have some extremely high values. Extremely high values exist, perhaps less common. Less common, but still exist. Okay, meanwhile, if that's the middle, you don't have no values that are extremely low. All right, and so an example of something that is skewed right would be income distributions. Okay, so we can probably say most people, probably 99% of people, make between $0 and $200,000 a year. Okay. All right. So this might be 0. This might be 200,000. Okay. Are there some people who make $1 million a year, $5 million a year, possibly even more? Yes. Okay. It's there are certainly people at the extremely high side. Okay, maybe not a lot, but they certainly exist. Okay, and they're they're way out here. If this is 0 and 200,000, then $1 million is 5 times this distance. So that would be 1, 2. It's actually off the paper here. So $1 million would be way out here. So that's something very extreme. On the other side, can you make less than $0 per year as a wage? No, you can't. Okay, I mean there might be some people who are in serious debt and in big trouble, but as far as you're being paid, you cannot be paid less than $0. Okay, so 99% of people might make between 0 and 200. Some people make 1 million or 10 million a year or more. So you have extremely high values, no one on the extremely low side. So that's skewed right. This over here would then be skewed left. And this is just the flip side. Most are on the higher end. You have some extremely low values. Okay. Let me just say a couple more things, and then I'll let you out of here. So far, all of our distributions have been unimodal, meaning that they've had only one peak. Okay. You could have something called with two peaks, and this would be bimodal. Okay. So perhaps we surveyed people who recently ate at Chipotle, and we said, when did you go to the restaurant? Okay, when did you eat at Chipotle? You'd probably see a bimodal distribution. Okay, you'll see two peaks, one around lunchtime, so one around noon, and then one around dinner time. Okay, with a kind of a fewer number of people going there around 3 or 4 o'clock. More of them around noon, more around 6 p.m., 7 p.m., something around there. Okay, so that would be something bimodal. If you have more than that, you would say multimodal. Okay, we'll end there. Have a good weekend, you guys. We'll see you guys. We have a holiday weekend, so we'll see you guys on Wednesday. All right.